So hi there guys. So here I'm going to show you how you can run decision curve analysis code to be able to get the results that we got as well. So let me share that with you right now. So if you go here to this site on Memorial Sloan Kettering Cancer Center, you're going to find this site over here. So if you look up decision curve analysis in Memorial Sloan Kettering Cancer Center, you're going to see decision curve analysis is a simple method for evaluating prediction models, diagnostic tests, and molecular markers. So then what you're going to do is you're going to go down here, and then if you click download R code, then what you should see is the following. You should see that once you download the R code, you're going to have DCA help file or all of these files here. So I downloaded the R code here, and if you click it, then you're going to have basically you're going to have this R code, and this R code is going to be DCA function, loading required libraries, keeping all of this information here. So basically you have access to this once you download this R code here. And I'm going to show you an example that they provide us when you run their code. So let me just pull this up right here. So similarly, if you put this R code in the that they provided in RStudio, you will get this result here. And what you will do then is you're going to see how if you run this. So right now the environment is completely empty. So I'm also just I'll clear all plots as well. So you can run this function here. And then, for instance, they provide an example in their code of using this MAS package, Memorial Sloan Kettering Cancer Center. And if you use this MAS package, and then you come up with some general linear model, some binomial logit function using this data set, and then this data set looks something like a low age, LW2 race, smoke, other variables here for this MAS package. Then you can come up with a predictive model here. And then you can perform decision curve analysis. So they provide the same function, data, outcome predictors, and these are more for the plot that you get returned, and then the minimum Y, which is the net benefit value that you want. So you can just now see that we have this data set, we have this DCA that's been performed, and now what we can do is, we can run this model. And then if we run, we ran this model here, and then we can run this. So under the data set prediction low values, we have a set of predictions here. And we can then run DCA on this set of values and then see how this threshold probability, we can see if you treat none of the patients, it usually is at 0. If you treat all of the patients, then this is the net benefit of treating all the patients here in their example. And then this is the predicted low net benefit if you go with this model. So this is the net benefit from the two extremes of treating none. If none of all are predicted as class 0, predict all are in class 0, that's this horizontal line, the net benefit is always 0. This curve here is for all, says what is the net benefit if you treat all, if you assign all individuals or all data points to class 1, what is that? So you have two extremes, either all, you can assign all to class 0, which is the treat none. You can assign all to class 1 for y equals 1, which is the treat all, or you can use your predictive method here, which is what this is here. So this is an example of running their code that is provided by Memorial Sloan Kettering Cancer Center. So in our situation, the code that I have also shared and the data that I've also shared relates to using Memorial Sloan Kettering Cancer Center. And we have a model for one of our brain regions that's using the lateral temporal lobe. And the lateral temporal lobe of the brain sort of is this region here. So if we look up in the brain, this is the lateral temporal lobe. It's sort of like this location of the brain here. And we've collected data in the lateral temporal lobe of the brain. And we've built a predictive model to sort of predict between, if COVID-19 severity or not, like if for these patients, 50, so there are 100 patients here. So you can see 100 patients here. These are the actual outcomes. There's a patient, actually 50 who are severe and 50 who are not severe here. So what you see here is that we have 50 who are severe in actuality and 50 who are non-severe. So this is the actual outcome. So y equals 0 is not severe, and y equals 1 is severe. So you need to be in the intensive care unit for COVID-19. So these are the actual outcomes that we have here. So not severe, not severe, 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 not severe. So these are the different classes that we observe here. And that's the actuality. And then from my model, using the predicted probabilities for like the lateral temporal lobe. So it was one of the brain regions that we investigated, Professor Wang and I investigated for COVID-19 severity prediction. So we have used our prediction model that is using support vector classifier. It's just a predictive model and it returns predicted probabilities that an individual has severe COVID or not. So as you see here, these probabilities should sum up to 1. So if I take this plus this, all these probabilities will sum up to 100%, so or 1. So it's sort of like the breakdown. So for this individual here, we predict 99.99% chance that they have do not have severe COVID and a 0.01% chance that they have severe COVID. And these bars here sort of represent like the probability of them having severe COVID. It's just a data visualization technique. So when this bar is filled slightly, it's a low probability that they have severe COVID. So this right here is the probability, predicted probability that y equals 1. That's what that is, probability that y equals 1. That's what's given by this here in red. And over here, what you observe is that when it's 100%, we definitely know that they have COVID, but these are the predicted probabilities. And all of these, not severe and severe, this is py equals 1, is this column here. And this is py equals 0. And I just put the region here just because I was looking at multiple regions as well, like hippocampus, dorsolateral prefrontal cortex. So that's what this is trying to show here for each individual. What is the actual outcome for that individual? So as you can see here, not severe is always 0. I just provided both just for context. So if class is 0, then they don't have severe COVID. If class is 1, then they have severe COVID. They need to be in intensive care. So these two are just the same information. It's just a reminder of what these mean. And for each patient, based on their gene expression levels, I came up with a predictive model to predict if that patient has severe COVID or not. And then based on your threshold criteria, you can then assign the patient as having severe COVID or not. So you would look at the probability that the individual has severe COVID. And for instance, if your threshold is like 20%, then every single person with the probability greater than 20% would be assigned as having COVID. So for instance, if my probability threshold is like 20%, then what I would say is prediction. Then I can say if this probability is greater than or equal to this probability threshold value, then I'm going to predict severe COVID. Else I will say not severe COVID. And that's my prediction here. As we can see here, that's my prediction. So if I'm using a probability threshold, that's sort of how I can go about making these predictions. based on the probability thresholds, PT, that's what this is. So these are the predictions. So if it's above the probability threshold of 20%, it is severe COVID. Otherwise, it's not severe COVID. So if I use this threshold, but as you can see that if I adjust this probability, so Py equals 1, if it is greater than Pt, the threshold, then y equals 1. And otherwise, it's the other way around. So this should be greater than or equal to. So based on these results here, we can see severe COVID, not severe. If I change this to being like 15%, you might observe some other changes happening. Like let's say that I make this prediction probability threshold like let's look at what happens here for these ones. You know, if I 80%, and let's look at these ones, how these change. For instance, like let's say I raise the probability threshold to 90%, then these change to being like not severe COVID, for instance. You can notice a lot of other changes. So that's sort of like based on what threshold. So the probability threshold is at that point, if you have any prediction that's greater than or equal to this probability threshold, you predict class 1. So if if the Py equals 1 is greater than or equal to probability threshold, you predict class 1. Otherwise, please predict class 0. So non-severe COVID. So this is for the class 1, which is severe COVID-19. So you would be in the ICU, intensive care unit. So that's how it works. So we can keep on changing this, seeing how results change. Maybe if there's a 20% chance, 30% chance. And it really depends on you and your preferences for false positives and false negatives. So that's just what this is trying to measure. So based on this idea, what I did is I took this and I just kind of put it into a neater format that is needed by the code, which is just for the lateral temporal lobe, also called the LTL. I have the actual outcome. I have COVID non-ICU, which is class 0. I have COVID ICU, which is class 1, and I have the region here. That's what this information is. And again, just please note that this plus this equals 100%. So that's just a way of breaking down this information. And this is just the same information that I presented here as well. So you can see that it's just the same exact information right here. 99 and 0.001. It's just the same information. So this is updated predictions, DF, COVID, support vector, classifier, lateral temporal lobe after 4-fold cross-validation. That's just a fancy name for the model that I was using. And then now when I input this into my model here, so I just read, this is on my my F drive, my good old handy dandy little helper, and I'm very thankful for it. So I can read in this data frame here. So I just ultimately, I read this in, and like the first row, okay, actual outcome, 0. This is the predicted probability of the patient not being severe and being class 0. This is the predicted probability that that person is in class 1. So this is the Py equals 1. And this is the region as well. This is just additional. So then I just did this just for sanity check, just to make sure this is lateral temporal lobe. And I'm looking for the column that I'm looking for is just going, this is just telling me this grep function in RStudio, which is what I'm running it in, will just tell me 1, 2, 3, 4. This fourth column has, so I look in column names and it just tells me which column has the information out of all the column names, which one has COVID ICU 1. And then this is just me sort of pasting and updating the column name, which you don't really need to do. This is just me making sure as I was running it for multiple regions that I just remember that this is for the lateral temporal lobe. And now you can see that I have a predictive model that has the actual class. It has my predicted probability that y equals 0 for non-ICU, my predicted probability that y equals 1. So it has the actual and then my predicted probability. And then I can just run this DCA function that was provided by Memorial Sloan Kettering Cancer Center on their website. I can just run this code. And what I will get is I'm like similar to the example, I'm going to get a bunch of net benefit results as well. So when I run this, so you can see here, I just can run this. And the outcome, it asks me, what is your outcome? So I say that my outcome is actual. And what are the predictions? The predictors that I'm using are this. The predictor that I'm using is this. So just like how in this example, previous example, we saw like in data set, predict low was sort of like the predictions that were made from this predictive model above. This part here was used, this pred low was used here. And the outcome was low, that it was trying to predict low in terms of age and LWT. Similarly, I am trying to predict for my data frame, I'm trying to predict the actual, that's what goes here, actual, this actual column. And the predictor I will use is actually this column, COVID ICU 1 LTL. And then I do smoothest falls. I just keep everything basically the same that what they use. And then I added in a context variable as well. And then I can say it's directly from here. I have a print statement that I added in. And now you can see this is the model for the lateral temporal lobe. And this is the LTL net benefit here. So interventions avoided was given here in the code. So it returns a list in the arc, interventions avoided. Then it also gives the predictors, probability true, interventions avoided per 100 individuals. This is net benefit, and this is a probability threshold. This is treat all, treat none, and my model. So what it returns is a comparison for decision curve analysis. So this is the decision curve analysis for my predictive model using the genes from the lateral temporal lobe to predict COVID-19 severity. So if I use my list of genes, my predictive model has returned for these individuals, these predictive probabilities that they have severe COVID. If I use this model of mine, what is the net benefit? That's what this line tells me, the net benefit from using my model versus using a predictive model where all of the 100 COVID-19 positive patients are sent to the intensive care unit. This is one extreme. So I can send everyone to the intensive care unit. Then what would that probability be? Net benefit of sending all to the intensive care unit. This is one extreme. And I have zero net benefit on the treated, on the severe patients if I send no one. If I predict everyone is in class 0, nobody has severe COVID, don't treat anyone. So the code itself takes my predicted probabilities and it performs it on Memorial Sloan Kettering Cancer Center's R function that's based off of the Andrews and Vickers decision curve analysis methodology. It already gives me the net benefit curve of how does my predictive model do relative to the extremes of treating nobody, predicting everybody's in class 0, sending no one to the intensive care unit, this value, or predicting everyone has severe COVID, let's just send everybody there, let's not make any mistakes, let's send everybody there. So those are the two options that could really happen. And then, or versus those are two extremes. And then my predictive model, how does it provide net benefit? So if this is at a given threshold, and this is a threshold at which I will send patients to the intensive care unit. Like if this threshold is 40%, then if an individual for my predictive model has a predicted probability of severe COVID of 40%, I would send that patient to the intensive care unit because I think they have severe COVID. then that's what this net benefit of my model would be. So this is decision curve analysis. And it's based off of this ready-made formula, which is awesome. So then based off of that, because we see that, that this LTL and B, if we look at the structure of this, we see that it's a list. So I can get the net benefit values from here again, as we saw above, net benefit. And this just sort of compares the net benefit for a given probability threshold. This is my PT. This is my net benefit for a given probability threshold from treating all, predicting all y equals 1. This is from treating none, predicting that everybody is in class 0. And this is from my predictive model based on my predicted probabilities. So I would typically use at a given threshold the net benefit that has the highest, the model that has the highest net benefit, the outcome between the three. The higher the net benefit, the better the model would be for my threshold probability. So maybe it can change, maybe it can vary, but based on my preferences, I would select that outcome for my threshold that gives the highest net benefit. So it's really subjective, and this threshold is going to be what I prefer. But from this plot, you can sort of see already for any probability threshold between 0 and 1, my predictive model does the best compared to the two extremes. And again, these thresholds are sort of how you decide to assign patients to a given class here. So what do you predict based on the threshold probability? Based on this value being above or less than this value, what do you predict? That's how this prediction is made. If this cell here is greater than or equal to this threshold, then you predict severe COVID, otherwise not severe COVID. And then that's how this, and you do this for each of these, and you can sort of see if this changes from 1 to 2% to 3 to 4 to 5 to 6, like to 7 to 8. How what this changes, maybe even to 25, 30, 35, 40, even at 50%, for instance, you can sort of see how it changes. And that's what happens as you scan along. And as we make these predictions, we sort of see the true positive, true negative, false positive, false negative count. So this is just an example of how you can take a predictive model that essentially at the end of the day, all it needs, you need is just for it to have the actual outcome and then just the predicted probability of being positive. You don't even need this one. I just wanted to provide everything because from this one, you can derive the other because this is just equal to 1 minus this. That's how you get these values. It all adds up to 1 anyway. So you just really need this value. You just need this, and that's all you need. And you just need a region or some context for why you're wanting to do this. And the code itself for Memorial Sloan Kettering Cancer Center is like you can run the R code and then you will get like R types of results. And then eventually you'll sort of see how, you can try to generate this idea for the same idea for many other, many others. So I ran the same thing for all 3 brain regions, the dorsolateral. This is the LTL that we looked at right now. This pink one here. This is what we looked at right now. This one here. And that's what we have the plot for here, this one. And we also saw the treat all positive COVID are in ICU or treat none, where you predict that all of them have y equals 0, the two extremes, and then you can send them to the ICU or not. So that's sort of how you can do it. And then you can add in other models, and then you can collect the net benefits from these calculations, put it into a data frame, and then compare them in mass and see which ones do better. So that's pretty much the key idea for how I did decision curve analysis to get the results that I talk about in our paper and overall. And this is how you can run it. You just need that small amount of information about the actual outcomes for a set of patients and the predicted probability. And it should be classes 0 and 1. So I hope that this helped you. So please let me know if you have any questions at all. And I'm Sanya Kuller. Thank you, guys.